Hello everyone. In this video, we're going to take a look at the limits of piecewise functions. Now, there are two main ideas I would like to discuss. The first one is just a little bit of review on how we graph piecewise functions. And the second thing, and probably more important, is how we find the limit of a piecewise function. There is one thing that we need to be really careful of, but we'll talk about that when we get there. So first thing, let's take a look at an example. So here I have an example of a piecewise function. Now remember, what makes a piecewise function is that the domain is split into intervals. So in this case, all of our possible x values, all of those real numbers, in this example, they're split into three different pieces. So the top one, all those x values that are less than 1, those are being represented by the equation x squared, which is just a parabola. In the middle, at exactly one x value, at the point x equals 1, we have the value of 2. And then everything else, all the x values where x is greater than 1, is going to be represented by the equation negative 3x plus 2. And then eventually what we want to do is we want to find the limit as x approaches 1. And that seems like a pretty interesting question based on the intervals we have. Since we get this change of our function, it's occurring at x equals 1, it may be interesting to see what's happening to the limit there. But let's start by graphing this. So let me get some axes. So our interval is switching at the x value of 1. But to make sure that I get the full picture on what my graph looks like, I need to put a couple points on either side of that switch as well. So we'll do a couple points on the right, and then we'll go a couple points to the left here. Okay, now we do have multiple ways that we can graph a piecewise function. I can take a look at each piece individually and graph them, and then just only use the part that we need. Or another way that I like to approach this is if I want, I can create a little table of values for each of my different pieces. So let's start with one table of values just for our top equation. So just the x squared. And based on the interval that we have, this only works for the values that are less than 1. It is just less than, so we don't have the or equal to part, but I do want to start at 1, and then I want all the values that are less than that. So I'm just going to pick out a couple, and these are what I'm going to plug in. So if I do 1 squared is 1. Well, now remember this first point, we don't have that or equal to, so this is going to be an open circle. So we have an open circle here at 1, 1. At 0, 0 squared is 0. Negative 1 squared is 1, and negative 2 squared is 4. So then we have a point at 0, and we're filling out our parabola here. All right, so everything less than 1, so everything all the way from negative infinity all the way up until this point where we reach this open circle is represented by this piece of the parabola. So that takes care of our first piece of our function. Now in the middle, our interval is just x equals 1. So this is exactly 1 point. At the x value of 1, our f of x value is 2. So at 1, we have this value of 2, and this is just 1 point right here. Once we get to the other side of 1, we're going to make another switch, and now we're going to use our last piece of our function. So again, maybe I'll do a little table of values just to see what we have. And now based on that interval, again, I'm going to start at 1. I don't have the or equal to, so again, this is going to be an open circle. But then I want to start using values that are greater than 1. So we'll just pick out a couple that are bigger than that. So if we plug in 1 to that last equation here, negative 3 plus 2 is negative 1. So let's see, if I plug in 2, it's going to be negative 6 plus 2 is negative 4. Negative 9 plus 2 is negative 7. And the last one, we end up with negative 10. So let's see what we get if we plot these. So 1, negative 1. And again, I don't have the or equal to, so this is just an open circle here. And then I can use my slope to get our other points. We have 2, negative 4, and 3, negative 7. And we could keep going. So now let's talk about the limit. So the limit of our function as x approaches 1. And we want to find out what we have here. Now, as I said in the beginning, there's something really important we need to be careful of when we're looking at piecewise functions, especially the limits. The limit has to be the same from both sides in order for the limit to exist. So let's take a look at our left-sided and our right-sided limits for this function. So we'll do the limit as x approaches 1 from the left, and let's see what we end up with for this. So as we're coming from the left, so our x values are moving along here and they're approaching 1. What is our parabola approaching, since it's representing that part of the function? So as we move along and our x values are getting closer and closer to 1, it looks like my y values, my function values, are also getting closer and closer to 1. Now, not quite to 1 because we have that open circle, but that's what they're approaching. So from the left, our limit is 1. And now let's take a look at our right-sided limit. So the limit as x approaches 1 from the right side of our function. So what we're doing here is our x values are moving closer and closer to 1 from the right, and we need to take a look at what's happening to our line. So what's happening to our function values as we move in the same direction. So in this case, as our x values are getting closer and closer to 1, it looks like these function values are getting closer and closer to negative 1. And same idea, we don't actually have a point here, but our values are getting really, really close to that. So then this limit is equal to negative 1. So because our left-sided and our right-sided limits are equal to different things, this means that our limit that we wanted to find, so the limit as x approaches 1 does not exist. And so there's our answer. The limit does not exist in this case. The other interesting we can note is that our function is defined at x equals 1 though. There is a point there. At 1, our function is equal to 2. But because our limits are approaching different values from the left and the right, that means overall the limit does not exist.